Hello and welcome to another LeetCode video. Today we're going to be working on coin change 2. And this is a very popular interview problem, and this is also one that is really good to learn the fundamentals of DP. So we're actually going to go all the way from the top-down DP into the optimized bottom-up DP, and we're going to go one step at a time and explain everything carefully. So let's read the problem. You're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. Return the number of combinations that make up that amount. If that amount of money cannot be made, return 0. You may assume that you have an infinite number of each kind of coin. The answer is guaranteed to fit into a 32-bit signed integer, but we don't really have to worry about that because we're going to be doing Python. So let's get into it. So in the first example, we have 5 coins, and there are 4 ways to make up that amount, right? So it's 1, 1, 1, 1, 1 is one way, and then we also have 2, 2, 1. Then we also have 2, 1, 1, 1. Then we also have a 5, right? So notice duplicates aren't allowed. For example, if we have this, we don't want something like this as well, right? So we don't want this answer. So we want to make sure duplicates aren't allowed. And so one trick, just right off the bat, to make sure duplicates aren't allowed is to make sure that the coin you're using, like let's say your coins are this, you can just say like, okay, when I'm done using these ones, I'm never going to use a 1 again, right? So you're going to say, like, I'm going to use X number of 1s, let's say 3, and then after that, I'm never going to use a 1 again, so you never have something like 1, 1, 1, 2, 1. So your answer is always going to be increasing, and then that way you never have a duplicate, right? So if you have 1, 1, 1, 2, this is the only way you can have this. You're never going to have it the other way, because once you're done with a coin, you're never using that coin again. You can only use a bigger coin. So this is like the same thing as combinations. If you follow that, then you're never going to have duplicates. That's a pretty easy way to get around that. So let's look at the second example. So in the second example, we're trying to get 3, and we only have a coin of 2, so we can't do that, so it's not possible. And in the third example, we have 10, and we're trying to get 10. We only have 1 coin, so there's only one way to do that. So that is possible. So we're going to focus on this first example, and basically we're going to try to figure out, like, how do we build this? So we can actually get rid of this section here, to be honest. And we're just going to focus on this first example, this 1, 2, 5. And we are going to be building 5. Okay. So if you think about it, the way for the combinations, like what do you need to know to build up these combinations? Like, first of all, you do know that like these states do rely on each other, right? So if you use a coin, your target's going to go down. Like, let's say we use coin number 2 now, and we had a target 5. Now our target will become 3. So your states do rely on each other. So you want to think about how you can do this doing DP. And so let's think about how we could do this doing DP. So to do DP, we need 3 things. So let's write that down. We need a states, we need a base case, and we need a recursive case. And we want to try to minimize the number of states that we have, because that will make our problem the best complexity it can be. Okay, so for our states, what can we kind of do? And then obviously you want caching, because you can obviously get to the same answer. You can get to the same like target multiple times. Like, let's say your target is like, let's think about this, like 10, and you used up coins 1, 2, 2, and then you also used coins like 1, 1, 1, 1, 1, and you also use something like this. So when you use coins like this, you would have 5 left to go, and when you use this, you have 5 left to go, and when you have this, you have 5 left to go. But once you get to some state, like once you know you have 5 left to go, it doesn't really matter what you used. I mean, it does a little bit, but essentially you're getting to this, you know, in the same way multiple times. So caching is basically never going to hurt you. So we are going to want to use caching, but yeah, like depending on how you do this problem, you want to make sure that like if you get to the same answer multiple times, you don't have to like redo the work, right? So let's actually take this and let's get rid of that. Okay. So let's write this 1, 2, 5 one more time. And let's think about like what states do we need, and what, so if our target is 5 here, what states do we need? So we don't want to have repetitive coins. So like I said, if we use a coin, like if we have an index, like let's say we're over here, and our initial state will just start over here, and we can say we can use any coin. But once we chose not to use coin 1, we'll just say like, okay, once we chose not to use coin 1, we will never use it again to avoid duplicates, and then we'll be at coin 2. So our states here are actually going to be, so let's write this over here. Okay, so our states will actually be an index, and it will also be how much we have left, right? So like a target. Because if we use some coins, we're no longer trying to get to 5. Like let's say we use this coin, now our new target is 4. And so our states are an index and a target. And if we look at the constraints, that's doable. I think the constraints, I might have deleted them, but the constraints are something like 5,000 for one and like 300 for the other or something like that. So that's totally doable. So you can have like an n-squared solution here, or like, you know, like this times this would be totally fine. So that's our states. What's our base case? So our base case is going to be like, let's just think of all the base cases we can have. So for one, our target can be less than 0. Like we're not, the way I'm going to do it at least is we're not going to check for is the coin valid until we recurse. So if our target's less than 0, what does that mean? That means we have an invalid solution, right? So what do we want to return? We want to return 0 because we're trying to return the number of states to make up the amount. So if we have an invalid solution, we're obviously going to want to return 0 because that's an invalid state, right? Okay. What if our target equals 0? Then what do we want to return, right? So if our target equals 0, then we're going to want to return 1, right? Because that means we've reached our target. So that means we have one successful state. Okay. What about if our index in coins equals like the length of coins? What do we want to return then? Like let's say like for example we use coin 1, then our target is like 4. And then we say, okay, we don't really want to use coin 1 for the next state, and then we don't really want to use coin 2, and then we don't really want to use coin 5. Let's just say we did that. Now we have a 4 target, and we're out of bounds on the coin, so we can't use any more coins. And we already checked that the target is 0. So if we check both of these, that means now we can't reach our target because we don't have any more coins. So we want to return 0 here as well. So we want to return 0 here. We want to return 1 here when we have something valid, and then we want to return 0 here. Okay, so what's our recursive case? Like, what do we actually want to do? So this one's also pretty straightforward. Yeah, this is pretty straightforward, and you can do this in a few ways, but the way we're going to do it is going to make a lot more sense in how we are doing, like, if we follow this logic, then the bottom up will make a lot more sense, essentially. So we're going to do it this way. So we have two choices. So A, we can use the coin we have, right? And then what's our state going to be if we use the coin we have? So it's going to be of DP, and then the index is going to stay the same because we can still reuse the coin. But then the target is going to be target minus the whatever that coin equals, right? Or 2, we can say we're done with this coin. And then that's going to be DP of, if we're done with the coin, we have to increase the index. And then our target is going to be the same because we didn't use the coin, right? So these are our two states. And if you think about it, either one of these is valid. So this is kind of like a house robber where we have two choices and we have to, sorry, it's not a house robber. This is more like of a climbing stairs where you can do either one of these. And so the result is going to be A plus B here. Like we can either use the coin we have or we can be done with it and just move on to the next one. Okay, so now that we have the recursive case, now we kind of have enough to code up a memoization solution because essentially we know that we can either use the coin or we are done with the coin and that would give us a result. So like on every coin, and then what do we want to call this with? So we want to call this with DP at index 0 because we want to allow to use every single coin. And then what's our target? Our target is like whatever the amount is, right? Amount. Okay, so once you understand this, like how this recursive case works, this is going to be very important to understand this for the actual bottom up. So that's how you make this, that's how you make your coins not repeat. So actually it won't look like 2, 2, 1, it'll look like 5, and then it will look 1, 2, 2. It will be increasing order. 2, and then 1, 1, 1, 1, 1. And that's essentially what you're doing. So at every coin, you're just saying, okay, like let's say I start at this index. It's like I either use the 1, and then my new target is 4, or I don't use the 1, and then my new coin is, so if I did use the 1, my index will stay the same. If I don't use the 1, my index will increase, and my target will stay the same. And you just keep doing that, and you add both of these to get your recursive case. So that's your two solutions. You either use the coin, or you don't use the coin, and then you can never use it again to avoid duplicates. Okay, so now let's look at the code for the memoization. So here it is. It's pretty straightforward. So we have a visited, and we have a DP, and then here's our cases. So if the target is 0, that means we're returning 1 because this is a valid solution, right? This is one of the ways you can get 0 coins. And then if the target is negative, or if we're out of bounds, then we're going to return 0. because if we're out of bounds, our target is not 0 and we don't have any more coins to choose from. Then we also have the visited. And then finally, we do the things that I said where you just either increase the index and you keep the target, or you subtract the coins from the target because you just use that coin. And then finally, you return it and you call this on DP0. Okay, so now we need to figure out how to do the other version of this, which is going to be the bottom up. And so let's draw the bottom up and try to get an intuition for this. So what I'm actually going to do is I'm actually going to draw the bottom up for this amount 5. Okay, and so what we're actually going to need is we are going to need 6 columns. Okay, I know my columns are kind of bad, but it is what it is. Okay, so for these columns, so we have 3. Hopefully we have enough here. Might have to make them a little smaller. That's okay. Okay, there we go. So we have 6 columns. And now for the rows, I'm actually going to make 4 rows. And I'll show you. You could do this a few ways, but I'm going to make 4 rows. But you could also make 3. Totally fine. And I'll explain that. So essentially what we're going to have is our columns, and I'm going to index these. So our columns will be index 0, 1, 2, 3, 4, 4, 5, and these will symbolize the amounts, but the amounts will actually be in reverse order. You could do it, another way, and then our coins will be coin index 0, coin index 1, coin index 2, and then this is like a filler index that we're not really using. We just need the values. Okay, and so this right here is going to represent the amounts, except this will be amount. So we'll just say A equals 5, amount equals 4. Amount equals 3, amount equals 2, amount equals 1. So it's like the amounts are the indices in reverse. You could also make your amount equals 0 over here if you wanted to. Okay, and now this is going to be all the coins that you have. So this is for this problem here. So this is going to be, coin 1, coin 2, coin 5. Okay, and so these states are representing like, here's the amount I need, and here's the coin I have to start on. Right? So for example, here I need an amount 1, and I can start on the first coin. Right? So there's definitely a way you could do that. And then here it's I need an amount 1, and I can start on coin number 5. And then this filler, we're actually just going to initialize this filler to be, I'll show you here. So we're going to initialize this to just be all zeros. And I'll explain why. Or you could initialize it to be all zeros. But essentially, so the thing to recognize this is like our base case is over here. It's these 3 numbers. It's when the amount we need is 0, because that means we have a valid solution, right? So when the amount we need is 0, that means we've like hit our goal. So what we actually need to do is we need to set these to 1s. And this is like our base case for our DP. So it's going to be length, amount plus 1, and then it's going to be, the number of columns will be amount plus 1. And then the number of rows will be the length of coins plus 1. Okay. So if you think about it now, what are these things representing? So this is like, let's say, what is this exact thing representing? So it's representing the amount when the amount equals 1, and I have to start at the last coin, right? So if your coins is 1, 2, 5, this box is representing I have an amount equals 1, and I have to start at the last coin. And so the way to do that, there's 2 things you could do. You can either check, you can just like, remember in our DP, we can either not use the coin we have. So if we don't use the coin we have, what state is that? Like if we say like, we don't want to use the coin we have, so that state is actually down here. And that's why this filler is zeros, because if we don't use this coin we have, we actually like have no more coins to use. So that's why these are all zeros for now, to initialize this last row. So if you go down, so we can write that down. Down equals don't use the coin. And then we can also go right, meaning use the coin. So if we go right, we have to make sure that like when we use the coin, we're still in bounds. Because in this case, the amount is 1. If we use a coin 5, we're like out of bounds, right? So we have to check for whatever coin we have. Like if we're using coin 5, that means we have to go 5 to the right, and then we have to check, is that in bounds? And if it is in bounds, we have to take that value. So we have to do down. We're only going to go down 1 cell, which is not use the coin, plus the right, and that'll be the value of the cell. And so let's actually fill these out. I didn't want to do a dry run of the memoization because I think that's going to be a lot trickier, but this is going to be a lot easier to visualize. So here we have our amount is 1, and we have to start at coin 5. And remember, once we use a coin, we can never use it again, and we have to go from smaller to bigger coin. So that's why we're going down, right? Like once we use coin 1, we can't use it again, so then we use coin 2. Once we use coin 2, we have to use coin 5. Then after we use coin 5, there are no other coins. And the reason I use this filler is because I will be checking the left and the right, and so I just didn't want to be out of bounds there, but you can totally get rid of the filler and just check, like, if you're on your last coin, just write 0 for the down section. Okay. So we go down, and we have a 0. So we can't use another coin, obviously, because we have no more coins. That part makes sense. Like, we're on coin 5. Now, with amount 1, can we go right? Well, no, because we'd be out of bounds, right? So here, we would actually write a 0. Now, here, we're on amount 2, coin 5. We can't go down. So the down for all of these is going to be 0 because we can't go down from coin 5. So we just have to check the right. So for the right, if we go right, are we out of bounds? Yes, we are, because we're going to go from 2 to negative. Like, this will be, if we're on index 3, we would be on index 8, right? You're adding 5 to the index. You're adding the coin to the index you're at, and you're checking, are you out of bounds? So this would be out of bounds. This would be out of bounds. This would be out of bounds. And finally, this, if you go 5 to the right, would actually be over here. And so that's inbounds. So that's why you needed to make all of these 1s, because this is the base case. Okay. So now we filled out that row. Now let's do the row for the 2s. So now we're on the 2s. So let's go. We're going backwards again. So we're going up, and we are starting at the right and going left. That means that's why, like, when we go right over here, we're ensured to have all of these filled out already. So we have to be going, bottom up. So that's why we're starting over here, and we are going all the way up to here. And once we get there, that's our answer. Okay, so for a equals 1 and coin equals 2, like, if we go down, this is 0. And if we go right, we have to go right 2 this time, right? Because our coin is this one. So we have to go right 2, we'd be out of bounds. So this is 0. Then here, we go down, it would be 0. But if we go right, it's 1. So we're going to have a 1 here. Here, if we go down, it's 0. If we go right, it's also 0. So it's going to be 0. Here, if you go down, it's 0. And if you go right, it is 1. So that's going to be 1. Okay, here, if you go down, it's 1. And if you go right, it's 0. So we add them together, and you get a 1. And that makes sense, right? Like for 5, how do you get 5 with 2s? You can't, right? With only using 2s and 5s, you can't. The only way to get a 5 with 2s and 5s is you skip the 2s. For 4s, you could do it with 2s. For 2s, you could do it with 2s. And then for all these even ones, you can't. Okay, so now, or for all these odd ones, you can. So now we're on the last row. Now we're on coin value 1. So we want to go down, it's 0, and then we want to go right. So for coin value 1, we only go right 1, right? We go right the number of the coin. The coin is 1 here. Not the index, but the actual value of the coin. So we would go right 1, so this would be 1. Here, we can go down, that's 1. We can go right 1, that would be 1, so it's 1 plus 1, so we have 2. Then we go right here, nothing. Here, 2. Okay, same thing, right plus down, we'd have 3. And then here we have right plus down, we'd have 4. And this is our answer. This is DP of 0, 0, meaning you start at the first coin and you have 5 to go. So once you fill out this whole grid, the number right over here is your answer. And if you scroll up, the 4 is what you wanted. Okay, so now we can share the bottom-up code. And it's basically what I said. So here it is. And so essentially, you're just making a rows and a columns. And your rows and your columns, your rows are the length of the coins. Your columns is the length of the amount. And then we also have this filler, bottom row for the coins, just because we're going down. And then essentially, we're making every last value 1 because those are all the base cases. And then here we're just saying, okay, let's just initialize it to be the down value because that always exists. And now if we can go right, if right isn't out of bounds, let's also add the right value over here. And then finally, we return the value at index 0. Okay, so that's how you do the bottom up. Now we have one more solution to go through, and that's the optimized bottom up. So if you notice, for all of these, once you were building this grid, we're only checking the value here and the value here, right? So if we're up here, if we're on this top thing, if we're checking these values, like, why do we need this bottom thing anymore? We're never checking down here. All we need is 2 rows. We need the current row, and then we need the row that we built from. Well, it actually turns out you can just build your current row from the row that you built from. And the way that you would do this is you would do a little change. For this filler row, you would just initialize a row to this. And then you can just say, so let's actually go through this. So let's make a row down here. And then we can just say like what row are we currently on to visualize this better. So we're going to make a row over here, and this is going to be like our default row, our fill row, and we're just going to initialize it to all zeros and a 1 at the end. And we're going to see how we could build these up without actually storing the whole matrix. We can just store one row. Okay, so, and this is like the bottom, this is not super obvious. And I do think that for drawing, for bottom up, I really think you want to draw the whole thing and like visualize like how am I actually filling this out? Does this make sense? To get comfortable with it. And then once you can kind of like see it, then you can not draw it, but it'll help you like solve a lot of your mistakes. Okay, so we just make this fill a row. Now we need to fill out this row. So we can initialize our value to just be the value below it to start off, because there's always a value below it, right? So we're just going to say for like this value, we'll just initialize it to be this value. So we can initialize like this whole row. We can just say this whole row is equals to this whole row below it, because all of these values up here are going to be the same as the values down here. If we're just saying, let's just get the down part first, right? We're just saying, let's just get that down section first, then we'll worry about the right. So once we're filling out this row, we can just say, let's just take the old row, and that's going to give us all the down values. Now we have to get the right values. And if you think about it, if you get the right values, right to left, you can actually get those while just being on that row. So for example here, like what's this gonna, so this is where we have, we can write this again. So this is gonna be coin 5, and then the amounts are always gonna be 5, 4, 3, 2, 1, 0. Okay, so for coin 5, we can essentially just do it in place pretty much, because we can just look like, okay, for this is filled out, so we don't need to do this one. But for this one, let's just go right 5 times and see if we're out of bounds. So here we are out of bounds. Here we're also out of bounds. Here we're also out of bounds. So these were out of bounds. And then the one we're not out of bounds is this one. And then we would just say like, okay, well, that's that right value that we needed. We already have the down, right? We got the down just by copying it over. And so now we have the right value as well, which is 1. And so now if you see like that is the same row as up here. And now let's go up one more row. So now we are over here. So now our coin is 2, right? Our index is 1, but our coin is 2. So let's draw that. So it definitely is a little bit tricky, but so you could see like initially, these are all of the down values for this row, right? Like these are all of the down values. So we got all those right away just by leaving them in place. We're just saying, let's just leave those where they are. We don't need to change them, and we're just going to add to them if we need to. So now we're at coin 2, and let's actually see what we need to do here. Okay, so we start at the 1 index. Or remember, we don't need to do the 0 index. So at the 1 index, we're going to be out of bounds because we need to go right 2. Here, we're going to be in bounds, so this is going to change into a 1, right? We're adding the right value to whatever we currently have. Here, we're out of bounds. Here, we're in bounds. And here, we're out of bounds again because we're over here. So if you look, this row looks exactly like this row over here now. And then finally, we would go up one row, or we wouldn't really go up one row. We would just be more like an indexing. But now we could say like, okay, now our coin is actually coin 1. And our down values are copied over, right? Like all these down values are copied over once again. So now we just need to get the right values. So we would say, we'd start here. We'd say like, okay, is there a right value? We already have the down value. Yes, there is. Let's actually change the color over here. So this value would turn into a 1. Okay. Now, is there a right value? Yes, there is. So we need to change that as well. So this value would turn into a 2. Okay. Is there a right value? Yes, there is. So now that value would turn into a 2. Is there a right value? Yes, there is. So now that value would turn into a 3. And then finally, is there a right value? Yes, there is. So now this value would turn into a 4, right? You're essentially adding the right value to the value you have in place. And so once you recognize that this down value is literally what you start with, you can just take the right value and add it to whatever you have. And so now you could see that this row is exactly the same as this row up here. And so this would be the space optimized dynamic programming solution, because we only have one row now, so you can just do it in place. So once you recognize that, and for harder problems, you will even have something like, instead of only comparing down, you might compare like a few rows down, like you might compare 2 or 3 rows down. So you can recognize like I only need to actually store 3 rows or 2 rows. And this is how all the house robber optimizations work as well, right? You're only checking the last 2 elements. So then you can just say like, okay, well, I just saved those last 2 elements. I'm never checking super far. So that's the same kind of optimizations you make here. So we can look at the code for that as well. Yeah. So here's the bottom up, and here's the optimized bottom up. Essentially, we only have a one-dimensional array, but everything else is pretty much the same. Like this logic is pretty much the same, except now you're just doing it in place, and we're no longer calculating this down value that we did before. Because if you notice, this down value is always set initially, and then now all we need to do is check for the right value. So because the down value is always set initially, we can just say like, let's just leave it the way it is. And if there is a right value, let's update that and let's return DP0. So we can actually run all these just to show you really quick. So we can run the memoization. That should work. Yeah, so you can see it's like not as efficient as the other stuff. And so we can comment that out. Now we can run our bottom up, and we can do that. And it's a bit more efficient. And then finally, we can run our optimized bottom up, and it should be the most efficient, hopefully. Yeah, so, I mean, it's kind of hard to see on LeetCode, but it is definitely more efficient. So let's actually go over the space complexity for these. So for the memoization, let's just leave a little bit of space here. So for the time and the space. So for the time, all of these are actually big O of length coins times the amount. Because if you look, like this is length coins times amount, you're getting that here. This is length coins times amount, you're getting that here. And then this is also index target. Index is the length of the coins, and the target is the amount you're trying to get. So all of these time-wise are length coins times amount, but the difference is for the memoization, it is also length coins times amount, right? So this is the same thing for the memoization. And for the bottom up, it is also length coins times amount because you're making a 2D array. So I'd say 90% of the cases, bottom up and top down gives you the same amount of space, but just for these kinds of problems. And I would even say that like once the problems get harder, you can't really optimize the space. So I would say in terms of learning, like if you can just learn top down and be comfortable doing hard problems, that's like 90% of the work. And then I wouldn't even, like I don't do too much bottom up. I definitely think I should get into it more. I think it's good to know, but if you have to know something, like memoization is a lot more valuable and it's a lot more intuitive. Okay, and so the bottom up, this last one is actually our space is only length amount. So we don't have to do the length coins as well. So we could see how much we're saving here. So the length coins is 5,000. Actually, sorry. The length coins is 300. So we're saving 300. And the amount is 5,000. So technically, we're not even saving that much. That's why like you don't see a ton of, efficiency upgrades. But this is definitely one-dimensional, so it's obviously better, just not like a ton better with these constraints. But if the length of coins was a lot bigger, then it would be a lot better. But yeah, so that's going to be all for this. And I did want to add one last thing. I'll start providing my code in the description below. I'll just like add a Google Drive link or something, because if people don't know Python and they just want the code in like Java or C++, what you can actually do is you can actually just take the code I provide and just ChatGPT it to ask it to just give you whatever code you want. Like you can just say like convert it to Java or convert it to C or whatever you want. And so that might be helpful for you. That way, if you don't know the language, you can still learn the concepts, and then you'll get like the same logic that I have in just the code base of your choice, I guess. So I'm gonna start doing that. But yeah, it's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.